And we'll go from the present slide here. Now, the only announcements I know about, there may be some others out there that I've missed lately because I haven't had a chance to check email recently. But if you're interested in the volleyball team, which we have a very, very good volleyball team, they're playing in the tournament, the National Junior College, some sort of district tournament, this weekend, Friday, Saturday, and Sunday, up in Boaz, I guess at Sneed State Community College. So if you are up that way or want to go up that way, they'll be playing various times over the weekend. They haven't announced, I know, of the times. But they've got a really good chance at doing very, very well. Now, this next one is interesting, but I don't know very many details. But here's what the announcement said. It comes from a postdoctoral fellow at UAB, I think in microbiology or somewhere like that. She said she's in a new cohort of what they call the merit scholars. I don't know what those are, but she sounds like a very interesting type person, that very concerned. And she sent it to Dr. Wilson here at the college, saying that she thought maybe some of our students would want to know about it. Came across her desk that there is a one week summer opportunity happening somewhere. It didn't say where. For students who may be interested in, here's the thing she said, biopharma manufacturing career. I take that to mean manufacturing pharmaceuticals, okay? I assume that's what it means. They will pay the students $1,000 for 1 week to go up there, wherever up there is, and pay the travel to get there and back. So $1,000 for a week, that's not too bad. That's $52,000 a year, okay, rate, you know, and it's only for a week in the summertime. Now, I don't know any more details than that. The email that they sent, there was a website, web link that you could go to, and I'm sure give all the details. All else she said was the deadline is sometime in January. I don't know when in January, just sometime in January. And so if you are interested in that, it sounds like a mighty good deal to me, but maybe $1,000 isn't what it used to be, but that was would have been a lot in my book. What's that? I assume they're just hosting students and trying to get them interested in coming to work for them. I don't know who the company is, anything else, but that web link, I bet you'll get you there. So if you are interested, do you know who Dr. Wilson, Tracy Wilson is here at the college? Over in biology, yeah, she's chair of the biology. She's the one that forwarded the email, and she'll be probably able to forward it to you. Or I could probably do that too. I'd need to get your email address and things like that. But Dr. Wilson, if you see her ever, she might have more information than I do. All right. Any questions on anything we've covered so far? Okay, we're in Chapter 17, and we're not doing every section in this. We just started last time electric fields, which is 17.4. And we talked about what the formula was for electric fields. To remind you, an electric field is the electric force, or the Coulomb force, per unit charge. Okay? And they usually put a prime on that. That would be representing a test charge. Now, to remind yourself again of what Coulomb's law is, the force due to Coulomb's law is a constant called Coulomb's constant, or the electrostatic constant, Q1 times Q2 divided by the separation distance squared. And you see if you, and this of course is measured in newtons because it's a force, and this is a Newton per Coulomb. That would be the units for your electric field. And the other thing to remember about electric field is invisible. Okay, you don't know it's there unless you happen to be an electric charge. If you're an electric charge, you know you're in an electric field, because if you're getting pushed away, it's a depending on your charge, it's your like charge. If you're getting drawn toward it, it's the different charge. That's what a field is. It's a space around a charge that affects other charges. And here is example 1 on page, if there are no questions, on page 458. A positive test charge of 30 microcoulombs. So this is your, what? 30 microcoulombs measures what? Which of the symbols written above would be represented by coulombs or microcoulombs? Okay, the micro is just it's the Q. That's your Q or Q prime. You see, that's units of coulombs. Force is unit of Newton. Coulombs is the unit of charge. So that's charge. Now, to get it to something more usable, that micro is 10 to the minus 6. That's a millionth of a coulomb. So this is 30.0 times 10 to the minus 6 coulombs. Now, if you wanted to write that in actual scientific notation, you go one more unit to the left here, which makes it a smaller number, making this a bigger number, so that'd be 10 to the minus 5. But I'm happy doing that. Your calculator will take care of it perfectly fine. So a positive test charge of 30 microcoulombs is placed in an electric field. The force on it is, so now they give you the force on that is 0.600 newtons. Now this is 3 significant digits, 3 significant digits, okay? The question is, what is the magnitude of the electric field at the location of the test charge? So we're looking for electric field. And what's its formula? Written right above there. Electric field is right there. Right there. What's the formula? Force divided by charge. Okay? And in this case, our force is 0. Force is 0.600 newtons divided by the charge 30.0, or you don't have to put 0.30, times 10 to the minus 6 coulombs. For some reason, my pen is awfully slow. All right. Now let me describe to you how to do this in your calculator. Hopefully you're getting this down now, but just in case you're still a little shaky on it, here's what you do. You don't have to put all those zeros, just 0.6 will do. 0.6 divided by, now you enter 30. You don't have to put all those, any zeros after that. Divided by 30, but then for this you enter your EE or EXP, whichever your calculator uses, and then do a -6. Now, some calculators you have to put the 6 and then hit the plus minus key. Others, if they have the minus key in parentheses, not the subtraction key, but the minus key in parentheses, you can enter that first and then the 6, and then hit enter. What do you get? I know it's going to be a 2, right? Say again? I'm sorry, I can't hear. Oh, you don't have it? Neither one of you have a calculator. Well, it's not that hard to do without a calculator. So what I'm going to do to make it a little easier is I'm going to move this decimal one place here, and that would make it times 10 to, see, I made a bigger number, so let's make a smaller coefficient. Exponent. This one, I'm going to move the decimal one place that way, making a smaller number. So like I said, let's make that a -5. You increase that by one number. It's a negative number, so you increase it to be from -6 to -5. Okay. Now, 3 will go into 6 2.00 times. 2 because 3 will go into 6 twice. The 0.00 is to give you significant digits. Times 10, okay, when you're dividing exponents, 10 to the -1 divided by 10 to the -5, what you do the times 10, but subtract the exponents. -1, yuck, -1 minus a -5, okay? So this will be 2.00 times 10, and -1 minus a minus is +5. -1 plus 5 is 4. And that would be, goodness gracious, that would be 10 to the 4th Newton per coulombs. Okay? If you wanted to write it out, that would be 2 and 4 zeros after it. 1, 2, 3, 4. 20,000 newtons per coulomb. That's a pretty significant force, and that's how they put it in the book, the way I did it to begin with. 2.00 times 10 to the 4th newtons per coulomb. It's a pretty significant field. The force didn't seem that big, 0.6 Newton, but you see the charge was so incredibly tiny, that meant that was a pretty big field. All right. And they show in your text some things. Electric fields are used for many applications in electronics and elsewhere. Inkjet printers, how do they get that to go? You have fields that direct that jet, the ink, to point it out, and every letter is shaped by electric field. Also, your old-fashioned televisions that had big old deep screens with that big box in the back, the electric beams were sent through electric fields. Okay. Now, strangely, at least it seems like to me, they have this thing on lightning safety here, which is not a bad thing to think about, but why in this chapter? I mean, it really doesn't make a lot of sense here. But what if you're outside when a lightning storm hits? They say the Earth experiences about 25 lightning ground strikes every second. Of course, the Earth is a big area, a huge area. Each year in the U.S., approximately 400 people are struck by lightning. That's more than one a day, so that is a sort of a big deal, resulting in 100 deaths. That's 1 every 4 that gets struck dies. Okay, that's pretty significant in my mind. Many of these strikes take place on ball fields, golf courses, or other open areas. So what do you do if you're out there? Now, this guy is shown in a golf course. I sort of agree with part of it, but I would contend there might be a little bit better thing to do here. Now, if you're on a ball field or other open area, most of the time ball fields are relatively flat. So there's not really a good place to go. Okay? You don't want to, and what this guy is doing, the good part, he's not going for the trees, because the trees are more likely to get struck than he would be. What I disagree with what he's doing, the stooping down, covering his ears is merely because if thunder happens, it's going to be significant. So that's why he's covering his ears. The stooping down is a good idea too, but I wouldn't do it there. Most of the time, your sand traps are deep. I would go down to the deepest part of the sand trap, stoop there, cover the ears there. The lightning is far less likely to hit you there. Otherwise, go to the lowest area you can find. And like it shows, stoop down. Not even a bad idea to lay flat, okay? Just to get the least going. So move to the lowest section of the ground, crouch down, as shown in the picture. It says remove all metal objects from your body because that would attract, it's a good conductor of electricity. So if you have a bunch of keys and stuff like that, put them off to the side, far enough from your body so it's not going to attract the lightning. Avoid tall objects such as trees, hilltops, power poles, anything that sticks up, okay? Don't think under a tree you're safe, you're worse, okay? And if you're on a body of water, get back to shore as soon as possible because there's no dips in a body of water. You're on the surface, okay? If that's not possible, crouch down and move away from tall metal masts or anything else that would draw the lightning. Interesting they put it there. I shouldn't have wasted much time with it, but I did. Okay. I can't get the pages to turn right. All right, there is a problem set, 17.4. There's only 8 problems there, so do any of the odds, 1 through 7, whose answers you can find in the back of the book. Now, we just did one kind, this one. E is equal to F divided by Q prime. What other 2 equations could you get out of that if you weren't looking for electric field? From that one equation right there, what other 2 equations could you get? Okay. Do you like the circles or the triangles, or you like just solving them literally? Circle and triangle. So which you prefer, circle or triangle? I don't care. Name one. Circle, okay? All right. A dividing line and a multiplication line, okay? Now, notice you have one on top of the other, okay? The one on top always goes in the upper half. Then the E and the Q prime go down here. So this one shows E is equal to F over Q prime. That's that one that was given. You could also do F is equal to, cover the F, and what do you have? E times Q prime. That certainly works. Or cover the Q prime, and you have Q prime is equal to F over E. Now, the pen isn't writing consistently, sorry. That last one, just keep this in mind. It's the magnitude of the force over the magnitude of the charge. Because actually force and not charge, field, magnitude of the field, both of those are vector quantities. You really can't divide them, but that's why you deal with the magnitudes only. And that's all we were dealing with anyway, was the magnitudes. Okay. So that's it for problem set 17.4. Let's move on to section 17.5. All right, let's start on the clean page. All right, to clear it. Okay, to clear this? Okay. All right, just a little bit of background. Now, a lot of what we've talked about up till now has been charges. Charge here, moving charge, forces, fields, that kind of stuff. But what we're going to do now is start talking about current, which is moving charges, not static charges. So we're going to start talking about current. Current basically is a moving charge. There are 2 types of current. One is called direct current. Okay, direct current. Also called DC. You'll hear electricians say, is this AC or DC? Okay, DC is direct current. Okay, electrons moving in a wire produce a current in the wire. So electrons moving produce a current. Let me put that. Electrons moving produces a current. Okay? Now, when the electron current flows only in one direction, that's what we call direct current. Okay? Now this may seem a little bizarre, but it is indeed true. Okay? I'm plugged into the wall. This cord comes from the wall. This cord goes to my computer. I will guarantee you that the current flowing through here is flowing only in one direction. Can't tell you what direction, but actually there's two wires in there. One goes one way, it goes here, and the other always goes that way. The computer works on DC, direct current. You got a cell phone, calculator, DC, okay? Because when you go to charge those, there's some sort of black box or white box or some sort of box that's in between the plug and you, right? Your car runs on DC. Now, it actually generates some AC, we'll get to that in a minute, but it's converted to DC, direct current. Anything that runs on a battery, direct current. Battery sends charge one way, back to the other side, okay? That's why there has to be two wires in there, one to bring it in and one to take it out, okay? So that's what direct current is. We're going to spend probably a little more time with direct current than we will alternating current. We'll get there. So let's talk about what alternating current is. That's also called AC. Okay? Current that changes direction is called alternating current. Now that's a real alternating current. Now that doesn't mean it's going this way and then every now and then it goes here, but then mostly it goes that way. That would be direct current. If the predominant motion is in one direction, that's direct current. Well, alternating current is more like this. Just moving constantly back and forth, back and forth, back and forth. In fact, the electrons aren't moving very far at all. They're just going back and forth, back and forth, back and forth, back and forth. Okay? Coming out of the wall plug here, the lights, I assume probably the one in the projector also. Everything that's plugged into the wall that doesn't have some sort of box, that's alternating current. So pencil sharpener back there. Plugged into the wall, no black box, no box in between, alternating current. Okay. Now, you might say if the electrons are just doing this back and forth, how is anything energized? Well, even in direct current, okay? If I were to measure the motion of a given electron in this wire, it would be incredibly slow. Because even in the wire, the electrons bumping into other electrons or other sites are attracting it or other things. It's not a rapid movement at all. Even though, when I turn on a light, it seems like they come on almost instantly. Especially an incandescent light, perhaps more so than a LED or a fluorescent. But even then, they come on pretty quick. It's not the current flow necessarily that, certainly that's involved with it, but what it is the electric field. As soon as I hit the switch, the field is set up everywhere in the circuit. So it doesn't mean that you have to wait for an electron to leave the switch and make its way to every light receptacle or different ones to go to there. No. The field is set up almost immediately, almost at the speed of light. The field is set up, and then immediately the light comes on. Okay? Same thing happens with alternating. As soon as the switch is cut, all the current in the whole circuit starts doing this, so there's where the energy is. It comes from the field, not just the movement of individual electrons. Certainly they're involved with it, but that's not all there is. So that's what our two types of current. So we begin with talking about an electric circuit. So here's another term. Electric circuit. Okay? What this is a conducting loop. Actually, the most important word there, well, both of them are important, conducting and loop, in which electrons carry, and we're going to talk about, they're talking about a flashlight, so this is DC. The electrons carry the electric energy, and that can be transferred from a suitable source to do useful work. Conducting loop, carrying electrons, or in which electrons, my symbol for electron is E minus, so I don't have to write the whole word, that carrying electric energy okay, that can be transferred okay, the energy is transferred from a source to do work. Okay, now just a couple of things to remind you of. Energy, work have the same units. So the electric energy that is being carried by this loop, the energy that can then be transferred to become work. Like the electrons carry energy from the wire, through the wires to the light bulbs, producing light. That's the work they're doing, okay? A heater, a charger on a battery, anything that's doing work, that's it. Now they're talking about flashlights here, so I'm going to draw the simple circuit here, and it's I'm going to use some of the symbols we use, okay? I'm going to try to keep them fairly simple and direct. Okay? First, notice a source. You have to have a source. Okay? How they represent a source in a direct current is usually a battery. Now look at that. They have one long line and a parallel shorter line. There's a reason for that. This represents a battery. You may have more than one cells, and if you do, they may put a series of long line, alternating long lines and short lines. Okay? That represents a battery. The current comes out of the battery and at some point goes through what they call a resistor. Okay. Now, the one in the book actually shows a switch here, and I'll try to draw a switch as well. Okay. If you close the switch, the current moves. Now, you might say, what direction does the current move? And that's an interesting question, and it's a question that people almost argue about. It really doesn't matter. This is... Is it Emily? Okay, I thought so. All right. I will give you the sort of this classic definition, okay? Good deal, thank you. All right. Because I put the long line here, this is called the positive pole of the battery. And in fact, most batteries, if you look at them, there'll be a plus on one end, a minus on the other, okay? The traditional thing is for the long line to represent the positive end, the short line to represent the negative end. Now, what difference does that make? That creates a potential difference, and that's what a battery creates, a difference in potential between the electrons there. Now, we're going to get into this a little later, but I think I'll go on and hit it now. In what they call conventional circuitry, everything in physics moves from high potential to low potential. That's just the convention. So the conventional current would have the current running in this direction. And the symbol for current, sometimes they use little I and sometimes they use capital I. I prefer capital I, but this represents the current. Now this down here is the resistor. In the text, they sort of draw, this isn't just like it, draw a circle or something around it indicating it's a bulb, a light bulb. Okay, that's not exactly like it is here, but that's what it represents. That's called the load. This is called the, I don't want to get too detailed with it, let's call this the, they haven't given it a name yet. Let's just call it the battery. They call it the cell, okay, C-E-L-L. That provides the energy to the circuit. The current carries the energy through the charges, okay? The load uses the energy to do work. In this case, produce light, because it's a light bulb. But the way this is drawn, there wouldn't be any current. Why not? The switch is open. The flashlight doesn't come on until you close the switch. Now once you close the switch, now the current starts flowing. And the traditional thing, conventional current, flows from high potential to low potential. Now why do I keep saying that? Because in reality, the charge carriers are most of the time electrons. And since electrons are negative, they flow in the opposite direction. So this would be the conventional current from high potential to low potential. Okay, but the electron, the actual electron current, goes from the negative to positive because electrons are negatively charged. They are repelled from the negative side and drawn toward the positive side. Sorry, folks. If you're listening at home, it came as a surprise because it snuck up on me. Sorry. Okay. I'm not dying or anything. It's just a sneeze. Okay. It doesn't matter. All that takes is that the field is changing. The field is what carries the energy. The charges carry the energy. The charges move through it. It doesn't matter which direction you're saying they're moving. The conventional current goes from high potential to low potential. The electron current actually goes from negative side to positive side. It doesn't really matter. In an AC circuit, guess what? They're going back and forth anyway. It doesn't matter which is plus or minus. It doesn't matter at all. But we don't use that terminology there. It's just the charges are giving up the energy to the load to produce work or light or heat or whatever, and then going back to the battery. You're not using the charges. You're using the energy carried by the charges, okay? The same charge that leaves the battery here returns to the battery there, okay? It may take a while, but it does. The energy is what's being used. The electrons that go this way, they go back in this way. You do not use up the electrons, you only use the energy the electrons are carrying. So it doesn't really matter which direction they're going. Okay? Now, they finally get around to naming this. Rather than calling it a cell, call it a source. That's the source of the energy. Okay? The source of the energy quite often is the battery. And that battery happens because of what we call a potential difference, a difference in potential. Difference in potential or potential difference. Okay. This sounds like a really dumb question. Since there's no guys in the room, I think I can ask it without getting too... Have you ever had a battery in your mouth? A battery. If there are guys in the room, the odds are yes, they've done it. Okay, but you have more sense than that, right? Okay. But here's another question that may sound personal, so you don't have to answer it out loud. Have you ever had a tooth filling in a tooth? Okay, with the silver composite filling? Oh yeah, okay. And have you ever accidentally bit down on a piece of aluminum foil? No? Oh, okay. If you had, you noticed a jolt. What you had in your mouth then was a battery. Because you have silver in the filling and aluminum in the foil, and your saliva is an excellent, what they call electrolyte, a carrier of charge. And that's what it takes to have a battery. Two dissimilar metals, and they don't have to be metals, okay? In fact, carbon is quite often one of the materials. So that's not a metal, but it's, can still deal with charges. All right, let me find my book. I know it's here somewhere. There it is. Okay. Oops, wrong pen. Okay, there's my pen. All right. This is Kayla. Huh? Huh? Tiara, I'm sorry. There you are. I was one off. Okay. All right. So, if you want to do it, when you go home tonight, take off a little bit of aluminum foil and bite down on it just very gently with where your filling is. And when you come back, tell me what you felt. Okay? I can see some shaking your head. It doesn't really hurt badly, but it's really surprising. Okay? That is a battery. So a dry cell, a 9-volt, any of those, two different metals of some nature, okay? And then there's a paste or a liquid or something in there that acts as the electrolyte, the thing that moves the charges. Now, what happens in a situation like that, and by the way, the first battery that was recorded of being discovered, though they didn't know it was a battery at the time, was actually done by an anatomist, someone who studied anatomy. He was a guy, his name was Luigi Galvani, good Italian name, okay? Luigi Galvani was an anatomist who was studying the tissues, okay? And he was studying it in a dead frog. Been dead for a while, but been stored in formaldehyde, so it wouldn't stink any worse than formaldehyde, which really stinks in my mind. But it wasn't decayed. He had it in formaldehyde. He had cut off the leg from this dead frog, and he was trying to study and determine what tissue was what. What were the muscle tissues? What were the veins? What were the arteries? The various things, trying to separate them. And he was using a small pair of tweezers, and I'm just going to make up something here because I don't know for certain, but I'm going to say they were made out of steel, iron tweezers, okay? Holding it with that, and his probe, that little needle-like stick that he was using to probe around with, let's just say it was made out of copper, two dissimilar metals, okay? And what he did when he was first hold it, and touch the probe to the leg, egg-sized frog leg, it jerked, it twitched. He probably came close to having a cow, okay? He was absolutely, pardon the phrase, shocked by this, okay? It moved on him. He said, my word, I've just discovered life. Because this was a dead frog, the leg cut off from the dead frog, and yet I brought it back to life. What did I do? How did I do this? Okay? So he got all excited and found out he didn't really bring it back to life at all. But he wrote it up anyway because it was really remarkable. And one of his compatriots, a guy named Alessandro Volta, lived up in Lake Como, Italy, which is way up north in Italy, right next to the Swiss border. Okay? The reason I know that, my wife had professional meetings in Lake Como. Happened to be a week that it was between terms for me. So I got to go with her. And she carried our niece, her niece actually. And so while Karen was busy at the meeting, Julie and I got to travel around or walk around Lake Como, take a boat ride on the lake, take the tram, go over to Switzerland. The ice was chocolate. It was good. And just, had a good time. And as we were walking around, there was this, right on the lake, was this beautiful structure there. It wasn't super big, but it was very impressive. It was domed and arched and just a very, very pretty structure. And I said to Julie, I said, you want to go see what that is? She said, yeah, let's go see. It's pretty, isn't it? So we walked up there to it, right there on the lake, and it was a monument to Alessandro Volta. He lived and worked in Lake Como. And what he did, he took Galvani's discovery and started working with it, testing different metals and different liquids in between, and he found that whenever he had two different metals, just about always he could set up a potential difference between those two metals. And they would move charge from one to the other. Metals are good conductors of the charge, so they would move charges. The liquid is what they went through. And that's basically what a battery is. A battery increases the energy of those charges. On the positive side, it's high energy, negative side, low energy, excess electrons on the negative side, deficit on the other side, and it starts current. And he started, we saw in it was sort of like a museum too. We saw some of this early, he called the battery piles, because the piles stacked on top of each other, alternating layers of dissimilar metals, and made very strong batteries, okay? And he did many, many experiments with that. He did many other things too. We found out all the other things, but it was quite a nice experience. I'd read about Alessandro Volta all the time. I'd been teaching physics and physical science, but there I got to see his actual hands-on equipment. I didn't touch it, but I saw it, okay, just as he had left it. Okay, now, so that cell that we said at first we're now calling a source. That's the source of the energy that the charges carry to take to the load, to be used by the load, and then the charges return to the source. Okay? Now, let's go. Let me draw. Okay. Let me draw the same figure slightly differently, like they do in the book. A different figure. This is figure 1719 on page 461. And here's how they describe it. Here's where they put the battery. They put the negative up here and the positive down here. They don't draw it the same way I did. Okay? Now, I really wish they didn't do it this way, but we're going to do it that way. This is the battery in between. Okay? This is a pole of the battery, and this is a pole of the battery. And then in between you have the battery. And what's happening in there? They take electrons, low energy here, okay, and increase the energy for the electrons to high energy there. What does that is that chemical reaction that we were just talking about that happens in the electrolyte. Okay, and that's what moves the charges. Now, sometimes that electrolyte is something simple as salt water, anything that will carry a charge. In your car battery, y'all know what it is there? Sulfuric acid. That's why if you ever splash some of that battery liquid on your clothes, you have holy clothes. I don't mean what you wear to church. It will eat up the clothes. It will. Really major. Look at some of the mechanics you see. If you see little holes in the clothes, it could be from where the cigarettes burned, but more than likely it's where battery acid splashed on it. Okay? What's that? I can't hear. Oh, if it hits your skin, it burns you. Oh, yeah. Sulfuric acid is one of the stronger acids that we have, and it will create what they call an acid burn. Sometimes some of these shows, good guy, bad guy shows on TV, you'll have sometimes people splashing acid in someone's face and it comes out all disfigured because it's really serious, okay? Can cause blindness, all sorts of things. It's not a good thing to play around with. So this shows the electrons going this way, and they call this the electron flow. I'm going to put E minus, flow in this direction, going to the light bulb, and again I'm going to represent the light bulb like that because I can't draw a light bulb. Okay, and that's the high energy here. Because the battery has boosted up the energy here, and then once it goes through and the light bulb uses the energy to produce light, and then it comes back into the battery here, and it's low energy here. Same electrons. You haven't lost any electrons. It's just the energy has been depleted. Okay? The energy has been depleted. They go back to the battery, get boosted up again, and start the route again. It's the energy you're using, not the charge. Okay. Now this is likened to this next part. It's the B part of that same figure. And that's what's in this. So let's go to this slide. Oh, there was that thing. I thought all we had here was this. Just both of them here. So my ugly drawing is replaced by this. Okay? The low energy electrons come in through the positive because electrons are negatively charged. They're attracted to the positive pole, come in here, boosted their energy, go out with high energy here, go through the load, the light bulb, the heater, the whatever it is, uses that energy to do the work it needs to do. Low energy electrons come back, boost it up again. Now, what wears out? Okay, you actually have charges moving around inside the battery. And when charges move, you're depleting one plate and adding to another plate. At some point, this plate gets holes in it or something, and it can't support the same charge it did before. That's what happens in your car battery. Okay? Actually, some of those plates, they're lead plates, usually 6 of them in the battery, and one side is lead sulfate and the other side is lead, and the charges move from one to another. The plates actually dissolve. Okay? And when one of them shorts out, then the battery is no good. Takes them quite a while. Now, the good thing about a charged battery, when you're driving and stuff, you're recharging the battery, and so therefore you're sending the things back. But everything doesn't always go back the way it should, and some plates will develop weak spots and stuff, and if they break, then that shorts out the battery. Now, this is likened to a water pump. Now, here's what the battery is like the water pump. Now the water pump is pumping water up here, but what's happening when it pumps water up here? It increases the potential energy of the water. You've changed from this elevation to that elevation. Remember when I talked about dropping a book on a person's foot? More energy if it drops from high than if it drops from low. Okay? Don't drop it on people's feet, but if you did. Okay? So the battery is like the pump here. The charges are like the water here. And what the battery is doing is pumping and giving the water more energy up here than it had down here. Then the water comes down through here, turning the turbine, and you could have that making a light, playing a radio. It could be lighting a light bulb. It could be charging another battery. I mean, it's not very efficient that way, but sure enough, the water loses the energy, turns the turbine, and the turbine makes for new energy in a different form. And then the water is pumped back up again and again. Same thing that happens here. The battery is like the pump. It gives energy to the charges. The charges are like the water, okay? And the charged electrons, they lose their energy in the load. It doesn't use up the electrons no more than this uses up the water. The water is continually cycled here, okay? And then the low energy electrons come back in and are boosted up again, just like the same water is boosted up again there. Now, all analogies will fall apart if you try to take them too far. And here's where this analogy falls apart. What happens if you cut through the pipe here? Yeah, water spills out, okay? And things don't work anymore, okay? If you cut through the wire here, it's not that the charges spill out. Now, if you touch it, they enter you. But generally, it just breaks the circuit. Nothing works anymore. It's just like opening the switch. You break the circuit, nothing happens. You break the line here, and water spills out. So that's where the analogy sort of falls apart. But you see the purpose of the analogy. What's happening here? The battery is your source. It's the pump. It's the thing that gives the charges their energy, just like the pump gives the water their energy. Okay. Now, we hit one part of the circuit. That was the source of energy. Now we're calling it a battery. We're calling it the chemical reaction. We're calling it the source. Okay? The next thing we're going to talk about is the conductor. The conductor is the wire. And like I said, you have to have, okay, I may not have said it clearly enough, you have to have a complete circuit. You break the circuit, everything stops. So the conductor is the thing that connects. Sort of like the pipe here, except you break the pipe, the water spills out, you break the wire here and everything stops because you no longer have a complete circuit. You've got to have a complete circuit. So that's what the conductor is. The conductor is the material. Now it can be a variety of materials. The most common is copper. Okay, we'll go over that in a little bit. Through which the charge is transferred. Okay, that's what the conductor is. The material, for instance, copper, through which the charge is transferred. Now, every material, pretty much, will transfer some electricity. Some materials are terrible conductors. So bad we call them insulators. They prevent charges from moving. But other materials, like copper, are very good conductors. There's one conductor that's better than copper. Silver. Well, there are probably some others too, but silver. Silver is slightly better than copper. Why in the world don't we use silver in our wiring rather than copper? It's a better conductor, only a little bit better, but it is better. No one has an idea? I take it you haven't bought much silver. It's very expensive. But that's only one reason. The other reason, copper bends really easily. It's a flexible metal. Silver is fairly brittle. You couldn't have a wire like this easily with, you could if it was thin enough, but it tends to be more brittle. So copper is just overall far better. Not as good a conductor, but only by a little bit, but much more, it's much cheaper and it's easier to work with. Okay? So that's what your conductor is. Now, if it's not a good conductor, it's called an insulator. Substances that do not allow electrons to pass readily are insulators. That was substances that do not allow charges or electrons to pass readily. The key word there is readily. Okay? If they just allow a little bit, they're poor conductors or good insulators. Okay. Common insulators are things like rubber, wool, silk, glass, wood. Distilled water, believe it or not, is a good insulator. Most of the time we don't have distilled water. Most of our water always has something dissolved in it. If it's dissolved in it, it has ions. If it has ions, it's a great conductor. Okay? So don't be thinking that water could be a good one. I sort of wish they hadn't said that, but actually I would say not just distilled water, deionized water would be. Okay, dry air is a pretty good insulator. You get a little bit of moisture in the air, though, especially if that moisture has things dissolved in it, becomes a much better conductor. When do you have lightning strikes? Usually when you have thunderstorms, right? When there's moisture in the air, that's when your lightning will strike more commonly. Now, there is a very small number of materials called semiconductors. Now, you may have heard of a whole area of California called Silicon Valley, semiconductors. They fall between conductors and insulators in their ability to conduct electricity. Typically, they conduct it in one direction, but not in the other. In some conditions, they will conduct, other conditions, they will not. So they're conductors sometimes, insulators other times. That's why they call them semiconductors. Now, remember I said copper is almost the best, or silver is almost the best? There are actually a few materials that are even better than silver. And these are called superconductors. Okay? Now, superconductors have fascinated scientists for probably, I'm guessing, about only about 100 years that we've even known about them. Heike Kamerlingh Onnes, okay? They don't tell where he's from. It seems like he's Dutch or something like that. Maybe Scandinavian, I don't know. Maybe, the name sounds like it could actually be Norwegian. Somewhere up there, he discovered superconductivity shortly after he discovered how to liquefy helium gas. Now, does that mean anything to you, liquefying helium gas? Helium is the second lightest gas there is, and it doesn't react with anything, even with itself. So in order to get it into a liquid state, you have to cool it to incredibly cold temperatures. I mean like just a few degrees above absolute zero, maybe 10 or 15 degrees. It has to be incredibly cold to liquefy. Well, he figured out a way to liquefy helium gas, and then almost immediately discovered superconductivity. There was a material, I don't remember what his was, that was not a particularly good conductor at all until it got to very low temperatures, and suddenly it became a superconductor. It hardly had any resistance at all. This has fascinated scientists ever since. There's been, I would say, at least 4 Nobel Prizes for different people who advanced this field of superconductivity in the last 100 years or so. It's pretty amazing. All right. He determined that mercury metal, which is not a particularly good conductor in the first place, lost its resistance completely to the flow of electricity at temperatures just above 4.2 K. That's 4.2 Celsius degrees above as cold as you can possibly go. Cold as you can possibly go. 4.2 degrees Celsius above that, we call that 4.2 K. That's the boiling point of helium, which is also the liquefying point of helium. Scientists are currently finding other materials where superconductivity exists at higher temperatures, and that's where the search has been and where different Nobel Prizes have been won. 4.2 is awfully cold. Incredibly hard to get anything that cold, but then when you do, it can become a superconductor. They've now got some that are up maybe as high as 35 K, which is still awfully cold, but that's more in the range of liquid nitrogen, which is much easier to do than liquid helium. Okay, higher temperatures. All right. The next topic here is the load. Okay, the load in the circuit converts the electric energy into other forms. Converts electric energy to work or other forms of energy, like light, sound, other forms of energy. That's it for load. So we have the source, that's the battery, that's the thing that gives the energy to the charges. You have the conductor that carries the charges. You have the load that uses the energy. So to tie this together, we now talk about the thing called current. The flow of electrons or any charge through a conductor is the current. Flow of electrons through a conductor is called the current. That's the current, the flow of electrons. Okay? Electrons do not collect and remain in the load. They continue back on the low energy side of the battery, energized again for another trip through the circuit. Okay, so that flow of electrons is called the current. Now, there is a unit for the flow of electrons. Okay, let's get away from calling it electrons and actually name it charge. Okay, I want to remind you of something that we've done. Way back in the first chapter, we talked about moving a distance or displacing. Time rate of change of displacement was velocity. You changed distance in a certain time. If you did it at a very low time, that was a very low speed. If you did it real quickly, that was a very high speed. Time rate of change of position is velocity. Time rate of change of velocity is acceleration. Now, up on that gas pedal, and you change from 0 miles per hour to 60 miles per hour pretty quickly. Your gas gauge goes down, but you do it, okay? That's acceleration. Time rate of change of, and we didn't talk about this term, but momentum, that's a force. Time rate of change of energy is power, okay? Time rate of change of anything usually produces another thing of interest. So the thing we're dealing with here are charges, okay? And charges, so current is the time rate of change of charge per unit time, okay? Now, what do we measure charge in? We measure charge in coulombs, capital C coulombs. What do we measure time? Seconds. What do we measure current in? Amperes. Capital A, named after Louis Ampere, a French physicist who studied early stuff with current. They named the unit of current after him. So an ampere is a coulomb per second, time rate of change of moving charge, okay? And that's the block at the bottom of your page 462. Let me see if no, we're not quite there yet. So I'm running out of room here. I'm going to go on and delete this. Is that all right? Not the whole slide, but at least the writing. Is that okay? Okay. So let's put that. Okay, 1 amp, and the term is ampere, named after Louis Ampere. The symbol for it is capital A because it was named after somebody, is 1 coulomb of charge, named after Charles Coulomb, so that's capital C, in 1 second. Well, that's not named after anyone, so that's a lower case s. An ampere is a coulomb per second. All right. Now I think we're ready for the next slide. Not yet. Close, but not quite there. Okay. Now, up till now, they've called the current, they haven't named it the current, but that's what it is. This measures current. Now, they use they put a statement here in italics trying to bring your attention to it. Here they've been saying electron flow is this way from high energy electrons at the negative pole to low energy electrons at the positive pole. From now on, they're going to flip that around. And what they say here, in this book, we assume that the charge carriers are positive. We know they're really not, okay? But the charge carriers aren't the important thing. It's the field and the transfer of energy. That's the important thing, okay? So from now on, we're going to say the current moves in the conventional method from high energy, high potential to low potential. So we're going to flip that around again, okay? And I'm going to use the next slide even though they don't mean for you to. The electrons would actually move from negative to positive, but they're saying the current moves from positive to negative. High potential to low potential. Everything else in physics does that, so they're going to do it here. The only reason electrons move the other way, they're negatively charged. What a shame. Okay? So, the picture in your book does this a little bit better than this one does, but it's pretty close. Okay, now that leads us to another thing. We've seen that current flows because of the difference in potential of your source. That thing that pumps up the charge, pumps up the energy. That potential difference is called the voltage. So we're not quite ready for series circuits, so let's go back here. This is your potential difference here. Okay? And what it measures is the change of energy or work, okay, because it's either one, work or energy, they're the same units, okay, over per charge. Okay, that's what potential energy. How much charge are you, and I mean, how much energy are you giving each one of those charges? That's what this is doing. You're pumping up the energy of the charges. That's your potential difference. Now, most of your batteries, if you got a battery like a flashlight battery, they're usually about 1.5 volts. Of course, a 9-volt battery will be 9 volts. Your car battery is probably going to be something on the order of 12. And if you had a big truck, that may even be up to 15. If you had something like a bulldozer or something, it may even be up to, up to 24. Bulldozer may even be up to 36 volts. But that's what your potential difference is. It's measured in volts. Okay? And 1 volt is, potential difference is this is 1 volt of potential difference, is 1 joule of energy. Symbol is J. Okay? The unit here is volt per 1 charge, 1 coulomb, which is C, 1 coulomb of charge. How much energy are you giving in volts and joules are you giving those coulombs in the charges in coulombs? That gives you your potential difference in volts. Named after guess who? Alessandro Volta. That's why it's a capital V. Okay? When you write out the word volt, it's usually lowercase, but when you abbreviate it, it's capital V because it was named after. A joule named after James Prescott Joule, and a coulomb named after Charles Coulomb. So all of those are capital letters. Okay? Now, this book uses an older terminology that you need to get used to, and that is what they call EMF. Now, no one even says what that stands for anymore. They just give it the symbol capital E. Now, I don't like that because most of the time we use capital E for energy. But in this case, they're using E for EMF. Now, here's why they don't tell you what those stand for. It used to stand for electromotive force. But guess what? It's not a force. That's a really lousy name for it. So they just call it E for electromotive, or EMF. That's what they call it, EMF now. Okay, that's measured in volts. Now, here's a problem here, folks. We also use the symbol capital V to stand for voltage. Okay, that's the parameter for voltage, but it's also 3 volts. That's the symbol for the unit. We use the same parameter for the same symbol. It's the same letter for both of them. So that's the one place it's up. There are other places you have things, like you have 1 meter is a distance, but you use little m for represent mass. That has nothing to do with distance or meters, okay? Well, here, this has to do with the same thing that has to do with. That's the unit to measure voltage, is the volt, okay? And we use the same symbol for both of them, unfortunately. That's why the book likes to use E, so you don't confuse it with the V. But then that E stands for electromotive force, which is not a very good name either. So anyway, it's sort of a little confusing, but it's really pretty simple. So Alessandro Volta, physicist born in Italy, Lake Como, Italy, in fact, and that's where he did his work. Now, there's one other issue here that we have to deal with. Let's talk about what we got. We got the source of the energy, which now we call that energy the potential difference, the change of energy per unit charge. That's the voltage, okay? That's the potential difference. That's what your battery or your source is supplying. We have the conductor, which carries that energy. We have the load, which uses the energy. We have the current, which is the carrying of the charge. It's the movement of the charge is the current. The voltage is the supplying the potential difference to the energy per unit charge. And one other thing that we haven't hit, and you have to keep up with it, and that's your resistance. Okay, remember when we were talking about rolling a bowling ball down the floor? It's not going to roll forever. Why? It's meeting resistance. Friction on the floor, air resistance, there's always resistance. Well, guess what? In electric circuits, unless you have a superconductor, which has no resistance, you are going to have resistance. Okay? Not all substances and not even all metals are good conductors. Even your best conductors, except for superconductors, have some measure of resistance. Okay? The opposition to current flow. That's what resistance is. Opposition to current. I can't write. Flow. Remember, the flow of charges, the movement of charges, anything that opposes that creates resistance. Okay? Now, the guy who did the early studies on resistance was a German physicist named Georg. It looks sort of like George, except it doesn't have the E at the end. It's Georg, and his last name was Ohm. Okay? And he did a lot of the early work with it, defined it, described it, worked with it, came up with formulas, all sorts of good stuff. So they decided to name the unit after him. So a unit of resistance is an ohm. Now, when they spell it out, they put lowercase, O-H-M. What symbol should we use for it? For ampere, we use capital A because it's named after Louis Ampere. For volts or voltage, we use a capital V for volt because it was named after Volta. What would we use for the name an ohm? Oh, yes. Why wouldn't we use a capital O? Well, let's say we had 5 ohms of resistance. What's wrong with that? It looks like 50. So, no, we can't use a capital O. Well, other times when we've run into situations like this, what we quite often do, when we run out of letters in the English alphabet, we'll go to the Greek alphabet. So they did. And the letter corresponding to ohm, O in the Greek alphabet is Omicron. The trouble with Omicron, it looks just like an O. So we can't use that one either. However, the Greek alphabet has 2 letters that start with O, not just one like we do. Their other letter is omega. Have y'all heard of omega before? Ever heard of the phrase the alpha and the omega? Beginning and the end. Alpha is the first letter in the Greek alphabet. Omega is the last letter in the Greek alphabet. Omicron is right in there with mu and nu, right after our M and N, O, mu, nu, Omicron. That's right there. Can't use that one, but we can use omega. So that's why we use that symbol for resistance. It's a capital omega. Now, this has nothing to do with the subject here or anything you're going to do in your chosen field, sonography. But I did want to, since it's here, I'm going to mention it to you. The opposition to current flow is called resistance. The opposite of resistance, which is the ease of current flow, that's called conductance. So that term, exactly the opposite of this, is called conductance. conductance. And actually it's 1 over resistance. Now the symbol for resistance, the parameter is R, capital R. The unit is omega, meaning ohms. But the symbol for it, just like the symbol for mass is M, but the unit for it is kilogram, well, the symbol for resistance is capital R, but the unit for it is omega, named after ohm, because it's an ohm. Well, conductance is 1 over resistance. Okay. So they needed a unit for conductance. And there wasn't any one particular guy that stood out. Just everybody was using it, so they couldn't name it after anybody. So they didn't know what to call a unit of conductance. Can anyone hazard a guess of what they might call a unit of conductance? I'll tell you what they used. Conductance, they called it a mho. M-H-O. Where did they get that name? It wasn't Larry and Curly's friend. No, that's spelled differently. Where did they get this term for conductance named a mho? Sort of a strange sounding name. M-H-O. Mho. Where do you reckon they got it? Not named after anybody. Why would they choose mho? Yes, they spelled ohm backwards. And since it's reciprocal, they just said, well, let's call it a mho. Now, what unit would they use? They already use M for meters, so they don't want to use that. They use mu for micrometer or micro anything. Capital M is mega, so they've already got M's all over the place. What would be the symbol for a mho? You sure have got it. That's exactly what they did. There's not a letter in anybody's alphabet that looks like that. They just flipped an omega over and made it a mho because it's reciprocal of an ohm. Physicists are crazy, strange people, okay? They think really weirdly. So anyway, that's beside the point. You don't have to know that. But that's what we measure resistance in. The unit is the ohm. The symbol for it is the omega. Now, I'm going to erase most of what I put up there, but I'm going to keep a little bit of it. Okay? Let's erase this. Conductance you don't need to know anything about. I was just giving you that as a dumb example of how crazy physicists are. Okay. So, resistance. There are 4 major factors that enter into resistance. The first of these is temperature. Okay. Now, why would temperature affect material's ability to resist the movement of charge? That's what resistance is, operations current flow. Well, think of this. Every material, copper, iron, aluminum, silver, whatever you've got, if you increase the temperature, the molecules are moving faster, moving harder, okay? So therefore, when charge is trying to get through that, it gets buffeted more, so the resistance goes up. So an increase in temperature increases resistance, okay? And that kind of makes sense, okay? Increase in temperature results in an increase in Now think back of what we just said a little bit ago. How did they get superconductors? Dropping the temperature big time, way, way, way cold. And suddenly something will become a superconductor. Now let me give you just an example of how they actually use these semiconductors. Now this is an amazing example in my mind. Japan has some of the best and biggest high-speed rail of any country on the earth, okay? And here's how they do it. They use superconductors. Now, if a material is superconductor, let me give you a hint for something we're going to do later. Anytime you have a movement of charge, you induce a magnetic field. So with a superconductor, which has absolutely free moving charges, no resistance at all, you can form some very strong magnetic fields. Okay? So by using superconductors, they can make some very strong magnets, and by using these in the rail lines, they actually raise the body up off the track, so you have no resistance to speak of. Okay, maybe some air resistance, but no frictional resistance at all, because the superconductor keeps it off the track. So those trains can go at incredibly fast speeds. Trains. Yeah. Okay. And those are high-speed bullet trains, they call them. Can really fly because they use superconductors. Of course, they have to keep those superconductors very, very cold, so there's a lot of energy spent keeping them cold, but they have them very well insulated and stuff like that. So anyway, temperature affects resistance. Number 2, the length of your conductor. Okay? Now, if every wire at normal temperatures, every wire, even copper or even if you had silver, it has some resistance. It's not a perfect conductor like a superconductor. It has some resistance. And the longer it is, the more resistance it is. I don't know if you've ever witnessed something like this, but when we were on the farm, this was several years ago, there had been a major ice storm went through. And in our yard at the farm are 4 huge, really old pecan trees. And that ice storm the water froze on the limbs and broke the limbs. And there were just huge limbs, small limbs, all sorts of limbs all over the ground. My brothers came over and we cut them up with a chainsaw and hauled them up. No one wanted them for firewood. Hauled them down to the woods and throw them into the woods. The big stuff. The little stuff we just raked into piles and then later burned when they dried out. Okay? When we went to burn, we wanted to have water nearby. So I got all the hoses that we could, but the first pile was a long distance from the house. So I got all the hoses I did and linked them end to end to end. And, we were going to use that to get water in case the fire got out of control. Well, when I did that, the longer the hose was, what came out of the pipe dribbled. I couldn't even get a good spray because there was more resistance to the long hose than there was in the short hose. Short hose, you got a good spray. Long hose, there wasn't enough pressure to give you any spray at all. You could hardly fill up the bucket in any length of time. So it wasn't a very good situation there. Okay, same thing true with the length of wire. The longer the wire is, the more resistance it has. Okay? We'll get back to that. So length of the conductor, it's so hard to get in and out. If we double the length, the resistance is double. The longer the conductor, the more resistance. Okay, higher the temperature, increase in resistance. Longer the conductor, more resistance. Number 3, the cross-sectional area of the conductor. What do you think on this one? Okay. You're using a straw in your cup there, right? Right? pretty good sized straw too, right? What if you had one of these tiny little stirrers that they use for hot coffee? What if you're trying to drink through one of those that was that long? Okay, and it may even hurt your eardrums because you have to do a lot of sucking to get it out, because the smaller the cross-sectional area, the more resistance you have. Because you see, what flows best is the stuff that's in the middle there. Anything along the edge is going to be slowed down by friction, but the stuff in the middle just glides right on through. So the smaller the hole, the closer you are to the edges, the more resistance you have. Same thing's true in a wire. The greater the cross-sectional area, the less resistance. This is an inverse relationship. Greater cross-sectional area, the less resistance. Yeah.
So, you know how you spoke about the longer you got your hose,
Yeah.
less water came out. Well, why isn't that the case with firemen?
What's this again?
Why isn't that the case with firemen?
With what? Fire?
Firemen.
Fire hoses?
Why isn't that the case?
Okay. Notice how big those fire hoses are. They're big, large cross-sectional area, so you have less problem with that. But they like to have the hydrant closer to where you are, you get more pressure. My insurance, at least it used to be this way, the closer you are to a hydrant, usually the better you are as getting good insurance rate. If you're a long way from a hydrant, that means they have to pump it out of the truck. If they can't get hoses close enough, so yeah, they still like to have it close. You still can get good pressure, but the closer you are, the better pressure. Same principle. Okay? But yeah, because it's a large cross-sectional area. This one right here. That's the winning factor there. Okay? But the closer you are to the hydrant, the less hose they need, the greater the pressure they get. And that's why it's to your advantage to be close to a hydrant, even though it's a pain in the neck. You can't park there because the fire hydrant's there. Okay. Okay. And therefore, the smaller cross-sectional area the greater the resistance. Okay. Okay. Now, the fourth thing is the material. And we've already sort of talked about this. Okay? Resistance depends on the nature of the material. Copper is a better conductor than steel or iron. Actually, the silver is better than copper, but just a little bit better. Not much better, just a little bit. And what we call is resistivity. Okay, and that symbol is rho. We use rho for other things too. It's the resistance per unit length. So you see the length comes into play again. Resistance per unit length. And that varies from material to material. Okay? Now, I'm going to give you an example of several of those. Let me just see what's the next slide is. Nope, still not there. You know how the old incandescent light bulbs work? You know what I'm talking about? Not the fluorescents, not the LEDs, but the old incandescent light bulbs. You probably still have some, but more and more people are using the complex fluorescents, which are those little spiral-looking things, or LEDs. But the old incandescent light bulbs, they don't even sell them very many anymore. Have you ever noticed them? Some of them will be clear, and you can actually see the filaments in there. Okay, you seen those? What do you notice about those filaments? Okay, there's sometimes 2 poles. Okay, I know what you're talking about now. There's 2 poles here. Some actually have 3. But then the filament is what's in between that. What do you notice about what's in between those poles? Number 1, well, I guess I'm going to do them sort of not necessarily in this order. Who invented the first light bulb?
Supposedly.
This what?
I said supposedly. Thomas Edison.
Thomas Edison, yeah. He was one given credit for it, and he worked and worked and worked and worked trying to get them to work, okay? Finally, he found the material, tungsten, that wouldn't burn out really easily. He had to evacuate all the air. If there was air, any oxygen around, it's going to burn out. It's going to bust the bulb, okay? So he filled the bulbs. All those were filled with argon gas, which is a non-reactive gas. It's a lot like helium. It doesn't react with anything, but it's argon. So most of all light bulbs are filled with absolutely no oxygen in them. That's why if you even took a pen and poked through that glass, the bulb burns immediately because the oxygen gets in there, the filament disintegrates. Okay? That's why every time you break a bulb, it goes out. Okay? Because oxygen gets to the filament. You probably had that happen.
Yeah, now that you said that, I get what you're saying.
Yeah. So he used tungsten because tungsten had large resistance. Unlike copper, copper wouldn't work well. Tungsten had a large resistance, and when you put current through it, it would heat up very quickly. And when it heated up, it would glow, and that's what made it a good light bulb filament, because it glowed a white light. So tungsten was the material. Why tungsten? It had a large resistivity. The material. It wouldn't work with copper. It certainly wouldn't work with silver. It wouldn't work with aluminum, but tungsten had a high enough resistance and resistivity that it would glow when it heated up. And that's how incandescent bulbs do. They get hot. That's why if you ever touch the incandescent bulb after it's been on a while, it is very hot. The fluorescents, they'll get sort of hot, but not nearly as hot as the incandescent. These LEDs, they don't put out very much heat at all, okay? So they're much cooler. That's why they're much more efficient bulbs. So there was material. But what else do you notice about that filament? It's about the thickness of a hair. I don't have much hair, but if you can imagine. If not, that's my hair. So you can imagine. It's very, very thin. So therefore, the cross-sectional area is tiny. So while the tungsten has a high resistivity, small cross-sectional area, it really has a lot of resistance. Now, what's the other thing you may have noticed about this filaments? If you ever look carefully at them, you'll see their coils. Have you ever noticed that? They look like little springs in there. Because when they blow, you'll see the little springs hanging there. Well, why do they do coils? That increases the length. Because if you're going from here to here, that's not very far, but if you make it go like this, that is, if you stretch it out, that would be quite a long length. Very small size, and a tough material. All right, so all three of those contribute to why an incandescent bulb works well. It heats up very quickly and glows, okay, because it has a lot of resistance. Because of the material, because of small cross-sectional area, and the long length. But here's the other thing. Now, not when you've broken a bulb, but most of the time when you have had a bulb go out on you, when was that? Think of times that the bulbs have blown. Not when you've broken it, other times. When you first turn it on. Now, why in the world would that be? Well, when you first turn it on, that's when you have the least resistance in the bulb, in the wire, because the temperature is low, okay? Because it's at room temperature. When you first turn it on, that's when you have the least resistance, So you get the most current through there all of a sudden. And if the wire, the filament is pretty weak, you get a lot of current through there real quickly, it blows. Most of the time when they're hot, the resistance is high temperature, high resistance, so therefore you don't have that much current flowing through there, so it doesn't pop on you. Now you can have, it's been on a long, long time, and it finally wears down, it can go out. But most of the time, just like you said, it's when you first turn it on, when the temperature is low, that decreases the resistance, so more current flows through. We haven't gotten to that yet, but that's why all those result because of changes in resistance. Okay. I think I beat that horse to death, didn't I? Here is the formula that relates what we were just saying here. Resistance. Now this is with a given material. Oh, okay. That's included in the row. That's the material part. Times L, that's the length part, but divided by the area because it's inversely related to the cross-sectional area. Now, this doesn't take temperature into account. You have to use a different formula for that. So that is how you get resistance out of your resistivity that varies with different types of material, length, which varies to how long the wire is, and A is the cross-sectional area of the wire. That's what we're going to use in the next example. So let me go back to the white page. Okay. So there was our formula. Whoa, I've got to get back to my color again. Okay. Resistance is equal to rho, which is the resistivity that depends on the material, times the length, which is how long the wire is, divided by the cross-sectional area. The bigger cross-sectional area, the less resistance, the smaller cross-sectional area, the greater the resistance. So that's why it's inverse relationship. So it says here, example 1 on page 464, find the resistance, that's R, that's what we're looking for. That's what we're looking for, of a copper wire. Okay, and copper wire 20.0 meters long. Okay, copper has a low resistivity, but goodness gracious, 20 meters, how long is that? About a quarter of a football field. Okay, that's a long wire, okay? 20 meter long wire with a cross-sectional area, so this is the length of the wire, with a cross-sectional area of 6.56 times 10 to the negative 3 square centimeters. Okay? Now wait a minute. What's a square centimeter? A centimeter is approximately the distance across your little fingernail. So a square centimeter would be about 2/3 of your little fingernail. Well, that's a pretty good sized area, but this is, break that into a thousandth of that. This would be 6.56 thousandths of a square centimeter. So if you were to take that little, about 2/3 of your fingernail and break it into 1,000 equal pieces, that's pretty small. Really, really small. So the cross-sectional area is this. Okay? Now they give you at 20 degrees Celsius, okay, now, there's nothing you can really use that, well, they don't even put the 0.0 in it. At 20 degrees Celsius, there's nothing in our formula about temperature. But that's where your resistivity is measured at, 20 degrees Celsius. So your resistivity, R, at 20 degrees Celsius for copper is goodness gracious, 1.72 times 10 to the minus 6 ohm centimeters. Oops. Centimeters. Okay. That's pretty small. Remember, copper is about the second best conductor you have, so it's a very, very low resistivity. So what's the resistance? R is equal to, and R will be measured in ohms. So let's see if that works. The resistivity is 1.72 times 10 to the minus 6 ohm centimeter times, oh boy, well no, we're okay. No, we're not. You got the length in meters. That's the bad news, because everything else is centimeters. So let's get this 20 meters, convert that to centimeters. Okay, now 2 blanks here, 1 blank for the number, don't worry about that. Put the units into place. 1 unit goes on top, 1 on bottom. Which you reckon goes on top? Meter or centimeter? 1 goes on top, 1 on bottom. Which goes where? You're absolutely right. Centimeters on top, meters on the bottom. Now you fill in the blank for the numbers. How many centimeters in a meter, or how many meters in a centimeter? There's 100 centimeters in 1 meter. Centi means 100, so there's 100 cents in a dollar, 100 centimeters in a meter. And notice the meters go out, and that leaves you with centimeters, so you're absolutely right. So this would be 2,000 centimeters, right? 1 0 from here, 2 zeros from there. Whoa! I said 2,000 and wrote 20,000. I don't know what's wrong with my brain. 2,000 centimeters. Okay? Yeah. 1 0 from 20, 2 zeros from 100, that's 3 zeros, 2,000 centimeters. So that's what we put for the length, 2,000 centimeters. Okay? And then we divide it by the cross-sectional area, 6.56 times 10 to the minus 3 centimeter squared. Okay? Now notice your units here. Centimeter times centimeters is centimeter squared. You got centimeter squared downstairs, so that wipes out, and that leaves us with ohms. So that's perfect. That's what we're going to measure this in. So someone's going to have to pull out your good old calculator. Do any of you have one? Oh, you do. Okay. Now remember how to do the scientific notation? Okay. 1.72 EE or EXP negative 6. Now remember how to do a negative 6? Some calculators, if you have a negative sign in parentheses, that's what you use, and do negative 6. If you have the plus minus key, that's what a lot of phones have, you enter 6 first and then hit the plus minus key. So you have to know which one you got. Okay? So 1.72 EE or EXP minus 6, however you get that, times 2,000 divided by 6.56 EE or EXP negative 3, or 3 plus minus, whichever you happen to have. Then hit equal, see what you get. What's that? Okay, now the phone probably has a different syntax than your calculator. So I'll help you with either one of them. Okay, you're going to use the phone. So it's 1.76, 1.72. Okay, now look for the EE or EXP. No, not E to the next. Okay, that's my name. Okay. EE, that one right there. Okay, then now you have the plus minus key, so that means you put the 6 first and then do the plus minus. Okay. Okay, now do times. Okay, that's exactly the number. 2,000 times, divided by, okay, 6.56 EE, and then it's 3 minus, I think that is. and you get 0.524, is that what you get? And we got 3 significant digits, so we can use that. I assume, yeah. So this is, read it out to me, 0.524. What's the next digit after 4? 3. Okay, we'll throw that away. 524 ohms. Okay. And in the book, that's exactly what they got. 0.524 ohms. So we just finished section 17.5. That's only had one example, but you can use this in several ways. You can solve for row, you can solve for length, you can solve for area, you can solve for all sorts of different things. Now, you won't be able to use the circles and triangles as easily with this, but because you have so many different things, you have 4 variables rather than 3. So I would just use regular solving for the letter. So anyway, do any of the odds, I'd say any of the odds 1 through 5, and then either 7 or 9. Okay, on the next page. Okay, now we talked about ohm, the unit named after him of resistance. That leads us to Ohm's law. Okay, we don't have a lot of time with this, so let's hit what we can on Ohm's law. And as I said before, his name was Georg, G-E-O-R-G. Middle name was Simon or Simon, and Ohm. He was born in Bavaria, which is part of what is currently Germany. At the time, it was probably a different country, Bavaria. And he did a lot of work on this, and he came up with a relationship called Ohm's law. Now, Ohm's law works for certain materials. Now, I'm going to hold this up so you can see it, because I don't draw as nice a graph as they do. Okay? And here is the key here. All right? For ohmic materials, which Ohm's law will work with, it's a straight line. When you plot the current versus the voltage, current is the flow of charge, okay? Voltage is the potential difference. Plot that, your slope comes up being 1 over the resistance. Now, if you had plotted the other way, voltage this way and current this way, then it would come out R. Okay, but they do it this way and make it 1 over R. There are other materials, for instance, semiconductor diodes. They are like this, okay? Very high resistance, well, let's see. High resistance down here, low resistance up here. That's non-ohmic material, okay? So Ohm's law only works for material that has that straight line resistance, okay? Not for variable resistance like you would find with semiconductors, diodes, and things like that. Okay, and here's what Ohm's law is. There's several ways to represent it. Here is one way. The current, by the way, current, the symbol for current is capital I. Where they get that, I have no clue, okay? But that stands for current. Remember, I told you that before. Some books use little I, this one uses capital I. Current is equal to voltage, remember. V can stand for the unit volt, but it can also stand for the parameter voltage divided by resistance. That's one expression of Ohm's law, okay? Where I is the current in amps, voltage is the potential difference, and guess what that's in? Volts. The unit is the same as the parameter. Strange but true. And this is the resistance. And that's measured in what you measure resistance in? Whose law is this? Ohm. And that's your omega, is your unit for resistance. Okay. Now, other places they will use, rather than V here, because that could be confusing, they would use E, standing for EMF. But that's not standing for energy. So that's why I don't like E as much. But this book uses it sometimes and sometimes uses V. Most of the time it's going to use V. Okay? Now, can you give me another way to write Ohm's law? There are actually two other ways to write it. You can do the circles and triangles if you want. Any guesses? R is equal to V over I, exactly, where the resistance is the voltage divided by the current. Or V is equal to I times R. Voltage is equal to current times resistance. See, V is always on top, so that would go on top of your triangle or circle. The I and the R is on bottom here, I is on bottom there, so that would go on the bottom of your circle, IR. Okay. 3 ways to express Ohm's law. Okay? Now, your units would be amp is equal to volts divided by ohms, or ohms is equal to volts divided by amps, or volts is equal to amps times ohms. Those are the units. They usually use the parameters for those. The book, they'll use the other. Now, they talk about, are we almost out of time?
Yeah.
Okay. They talk about an activity here, string of lights. If you want to play around with that, you can. We don't have time to do those would be fun to do. So what we'll do next time is start with the example 1. Okay? So let me first erase this. This last time I made it to example 2, or one time I made it to example 2. So we'll start with example 1. All right. No new problems there, but we do 2 examples here, and then you'll have lots of exercises to do, problems to do. All right, any questions? All right. Appreciate the 2 of you hanging with me for the full time. We were gaining and losing awfully slowly and had a pretty low crowd tonight to begin with, so appreciate it. What's that?
It's probably the writing.
Well, that may be it.
Can I get the one that you gave out last week?
Oh, you weren't here last week. Okay.
Unfortunately.
Okay, that was the one, okay, there was test 1. I've returned all those to people. Test 2, I'm still missing 1 person, so I can't return those yet. Did you see what you scored? Okay, I thought you were probably sitting on Blackboard. Okay.
You still missing somebody with that? You haven't had that one in a while.
What's that?
You still missing somebody with that test 2?
Test 2, yeah.
Yeah,
Well, he's says he has really bad asthma, and he's been in and out of the hospital a lot. So it's only he in the class, so I think he's. All right, here. Nope, that's not it. I don't think. No, that's the wrong one. Oh, that's it. That's the one you just turned in. No, this is the previous one. Here's the one you just turned in. Okay. All right. Here's the one I passed out last time. All right. Now, notice number 8. They're missing something. A train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds the whistle, but they never give the frequency of the whistle. So the frequency of the whistle is 585 hertz. That's what's written there. What frequency is heard by the observer? And assume the sound velocity in air is that. So that says the train is coming toward it. Number 9, the car is traveling away from you at 70 miles per hour. The car horn produces a sound at a frequency of, and they left it off. So that's 5,000 hertz. Okay? And what frequency do you hear? So that's the other Doppler effect. Okay. All right, good deal.
school?
What's that?
You ever teach high school? You ever taught high school?
No. Do I seem like it?
No, I think, putting you with younger man, I think it was just good idea. They're still shaping.
When I say I haven't taught it, I was a substitute teacher for just a few months in between when I got out of the Navy and started back to grad school. I was a substitute taught for about 6 months or so, but that's the only time I've taught in high school. Oh, yeah, actually, earlier than that, I did. My dad taught for a short time at a private school, and whenever I came home, he would have me teach in his place because he didn't like teaching. So I taught just little bits and pieces here and there. But no, I've never taught full time. What's that?
The experience will.
Oh, I see. Yeah.
So that's why I wondered that when you were talking. I wondered if you ever taught school.
Right.
Doing experiments.
Yeah. I've taught physics that we have done experiments, the ones that have labs with it. This one doesn't have lab time associated. Yeah. All righty. Well, have a good week. We'll see you next Wednesday.